Hi, welcome to B.Tech. In today's class, we will be dealing about antennas, arrays, and these arrays will be considered with point sources also. So that is n number of point sources could be forming as an array. When this array structure is been formed, as I said earlier, they are needed to be placed at a distance apart, and when they are being placed, the currents and the phase should be calculated or to be considered. Here we will be having equal amount of currents in major cases and the phases are going to get varied. But here we are going to study in what way they are being analyzed. So the first point here is arrays of 2-point sources, in what way they are being showing the variations in current and phase. The first thing is that when an array structure is being formed, we need to find it out the total amount of the field pattern in terms of adding the individual current elements along with the phase elements. So how many types we are going to have this in adding the field to attain this current and phase patterns? So we will be having one, equal amplitude and phase. The second one is equal amplitude and opposite phase, and the third one is unequal amplitude and opposite phase. So these are the three cases where we are going to have the consideration of currents and phases and to define the field patterns. And the first case is equal amplitude and phase. Here what is that is two isotropic sources are being taken and they are being placed in a distance apart in a Cartesian coordinate system, and they are being placed at equal distances. Remember that they are being placed at equal distances from the origin of a Cartesian coordinate. If you see the diagrammatic pattern here, I have taken a Cartesian coordinate axis x and y axis where I defined the origin point. From the origin point at a distance, I have placed one isotropic source and the second isotropic is being placed at the same distance on the opposite direction. So now the distance between these two. Now I will be showing you the pattern in what way we are going to place these two isotropic point sources. So I will be taking a Cartesian coordinate where I will be having x-axis as well as y-axis. I will be considering an origin point 0 and I will be placing one isotropic source at a distance from the origin and considering it as 1, and the other source, isotropic source, at an equal distance on the opposite side of the first one to the origin. So I will be placing the second source. Now from origin they are being placed at equal distance, remember. So what is that is, I will be taking a particular point at a distance from where I need to study the variations. So I will be drawing a particular straight line which joins this point. So here it is a point source till the distance where I need to study the plot. So the same lines should be drawn towards the point source. What happens is that we will be having three collinear arrays which are going to be present. And now in order to study the variation, what is that is, first we need to calculate the distance. So let me take that in always I will be saying that the isotropic sources are being at a distance d apart. Then what will be the distance from origin to the first source? It will be d by 2, and to the second source from origin it will be d by 2 itself. And the angle from the origin to the point source, if we consider it as theta, then we will be able to calculate the other sides also. So here the other side from the second source to the origin plane will be considered to be as 2 bar. So one side is been known to us, the other side we need to calculate it. And here also we will be having the opposite side to the generally you will be knowing that sin theta is equal to opposite side, that is 2 bar divided by the adjacent side, that is origin 2, and cos theta will be origin 2 bar to 0 2. In this way we will be able to note the things. But here, as point from origin to the point source, as we need to know, then what happens is 0 to 2 bar is nothing but 0 to cos theta. 0 2 is d by 2. So it will be d by 2 cos theta 2. So this is the distance patterns that we had arranged in this way to find it out the phase variations. Now, after seeing this, leave this particular diagram for some instant of time. After moving this, first we will be finding, as I said, the path difference between the two is needed to be calculated. What is the path difference? As I said, they are being aparted with a distance of d. So here we will be calculating d by 2 cos theta. Why d by 2 is being taken is that as we are being calculating the distance from origin to the point source, the same distance needs to be considered. So as it is d by 2 cos theta, with reference to the second source, I will be having another d by 2 cos theta with reference to the first source. So grouping together will give me the actual path difference. So I will be having d cos theta. In terms of wavelength, when I need to talk, that is d by lambda cos theta. And what is the phase angle? In what way it is been defined is, it is always 2 pi path difference. So I will be substituting the value 2 pi into d by lambda cos theta, which is nothing but beta d cos theta, where beta is considered to be as 2 pi by lambda. And now the main purpose of finding this path difference and the phase angle is that to find it out the field pattern. When field pattern is being considered, I'll be, as I placed the coordinates in opposite point sources in opposite way, one will be having E1 e power minus j 5 by 2 plus the other one will be having E2 e power j 5 by 2, which means that one source at right angle, the other source in the opposite side of it to the right angle. I'll be having this, and or simple terms, they are being 180 degrees apart. So that is the reason I'll be having one field pattern with negative, the other field pattern with positive. And as amplitudes are same, because in array structure we will be saying that the amplitudes will be equal. So E1 will be equal to E2 will be equal to E0. In such case, we will be having this notation, that is E equal to 2 E0 e power minus j 5 by 2 plus e power j 5 by 2 by 2. For expressional point of view, I has multiplied 2 and divided by 2, which is in the form of cos theta. So we will be having from trigonometric functions, we will be having this cos theta equal to e power j theta plus e power minus j theta by 2. So in simple terms, we will be able to write it as 2 E0 cos 5 by 2. Now substitute the value of 5. So on substituting, I will be having beta d cos theta by 2. So E0 term defines the amplitude, and where beta d cos theta by 2 defines the phase. So this particular equation will be helpful to us in finding out the radiation field pattern. So, and in normalizing to find it out the effective radiation pattern in a diagrammatic view, what is that is, we are going to normalize this expression. So to normalize this expression, what is that is, we are going to take 2 E0 as 1. So when 2 E0 is taken as 1, I'll be having E equal to cos beta d cos theta. So on the calculating it as d equal to lambda by 2, because I'm been using half of the wavelength, half wave dipoles itself, then lambda by 2 needs to be used here. On substituting the values, I'll be getting E equal to cos 5 by 2 cos theta. Now, to attain the maximum direction, so the directivity is always indicates that the with maximum will be attained as 1. So plus or minus 1 is being taken. Now the field pattern cos pi by 2 cos theta is equivalent to plus or minus 1. So it is the same trigonometric functions I am going to use progressive, that is pi by 2 cos theta max will be equivalent to plus or minus n pi. So here n could be 0, 1, 2 in such a way. If n equal to 0, then what happens is that pi by 2 cos theta max will be equivalent to 0. Now cos theta max will be equivalent to 0, which means that theta max could be either 90 degrees and 270 degrees. For minimum direction of cos function, it is said that it is 0. So the same cos pi by 2 cos theta should be equivalent to 0. Now in terms of it, I will be having plus or minus 2n plus 1 pi by 2. So on substituting the values, I will be having theta minimum as 0 degrees or else 180 degrees. Half power beamwidth points, that is half cos theta, cos 45 degrees will be considered to be as half power. So cos 45 degrees is nothing but 1 by root 2. So here we will be having writing it as 2n plus 1 into pi by 4. So we will be having theta half power point will be 60 degrees and 120 degrees. So this is of the first case where the antenna or the isotropic sources are being placed in equal amplitudes as well as in equal phases. The maximum will be attained at 90 degrees and 270 degrees, minimum will be attained at 0 degrees and 180 degrees, and the half power beam width will be attained at 60 degrees and 180 degrees. With this point, what is that is, we need to draw the radiation pattern for this. So for the first one of equal amplitudes and phase, the radiation pattern will be, so what is it? The minimum is at 0 and 180 degrees. So I will be considering 0. The maximum radiation is attained at 90 degrees. So I will be considering a dot here. And half power beam width, that is at 60 degrees, that is here. So what is that is? This particular structure. So here the variation is 60 degrees. 60 degrees will be here. So that if I am going to draw in that way, I will be having this radiation lobe, and we will be calling it as major lobe that is going to be attained, which defines the field pattern. So this is what. In this way, we need to define the radiation field patterns for an array of two identical isotropic sources which are having equal amplitude and phase. Thank you.